Better Thursday night than Friday night. So, okay, so we're just gonna think about, we were talking about pressure and how to think about pressure as those molecules drumming against a surface. So we're gonna think more about thermal properties of things, and we're gonna develop a very simple picture, and you've probably thought about much more complicated picture in your chemistry courses. Here I'm showing, for example, if we had, water, maybe a water solid or a water liquid or even a water vapor, and we wanted to draw something that was semi-realistic, we've got H2 and then the O, and, it sort of looks like Mickey Mouse ears on there. And that detailed structure is rather important, especially for the crystal structure of ice and things like that. There are lots of properties that depend on the exact shape of this molecule. And of course, the individual molecules are exerting forces on each other. And that the funny shape of the molecules determines exactly how they bond with each other. But for our purposes, we're going to think about large numbers of molecules and we're not going to be concerned too much about the crystalline structure, so how these things are oriented, but rather just about the overall densities and how they're moving with their temperature at the molecular level. So for the most part, we're going to draw individual molecules like either as spheres, or most of the time we'll be looking at two-dimensional pictures, even though we know they're moving in three-dimensional. And so for us, just to draw them as a little disk as a molecule, yeah, we're ignoring a lot of the structure, but we can still visualize that kind of movement down at the molecular level and think about what pressure is doing, what temperature is doing, those kinds of things, to think about a little, a picture you can have of thermal physics. Now, part of this picture seems to suggest something about some molecular forces. The fact that I'm drawing these in what looks like a hard sphere or a hard disk seems to suggest that they bump up against each other and they don't like to go closer than a certain distance, right? Obviously, that's not supposed to be a realistic picture of a molecule. So the idea is when you have a molecule, if it's neutral, it's going to strongly repel other neutral molecules because you've got nuclei in the middle and you've got electrons on the outside. And when these are far away, of course, they're overall neutral. They don't exert much of a force on each other. But when two molecules get close to each other, they're in a gas and they're heading towards each other and slam and bounce off of each other, the electrons get really close to the electrons. And the protons that are in the nuclei stay relatively far apart because the electrons are on the outside of the molecules. And so when they get when they get close together, they strongly repel each other. And that's supposed to be suggested by this sort of what looks like a hard sphere in our picture that I'm drawing there. What you can't see in that picture is that also molecules tend to attract weakly when you slightly separate them. So if I take two molecules that might form a gas or something like that, and I'm not pushing them together hard enough to change the chemical structure and form bonds, but I just push them, they bump up against each other, the electrons get near the electrons, they don't like that, they want to push apart. But when I separate them slightly, there's an effect of one molecule and the other adjacent molecule spontaneously polarizing, which causes them to attract a little bit when they're not quite so close together. So you can't see that in the picture. So you can imagine they really don't like to be close together, but if you try to pull them apart a little bit, they're a little bit sticky. They like to clump together. But of course, they're moving all over the place, and maybe they're moving so fast that they don't really pay attention to that tendency to clump too much. But the fact that they're overall neutral, right? If we've got a gas of nitrogen or something like that, and unless it's super hot, almost all the nitrogen atoms are going to be neutral. And so when they're separated by a substantial amount, it's just a neutral molecule and another neutral molecule. Electrically, they're not interacting with each other. So the hard sphere picture, we can see that they repel, but you kind of have to imagine that there's no force and that there's a slight attraction when they're just separated a little bit. So they tend to want to clump together as long as they're not moving too fast. Okay, a little bit of junior high school science here. What are the big phases? Of course, there are lots of different phases, exotic phases of things, but the basic ones you learn about early on, and all we're going to concern ourselves with here are solids. So when things are cool enough, that attractive force, and of course the exact shape of the solid here, this is just a notional picture of the solid. The exact shape of how things line up depends on that detailed molecular structure. But we can think of that attraction in a gas when things become cool enough that those things are allowed to clump together, and they're going to clump together in a certain kind of shape. They won't always make up something with sort of hexagonal symmetry like this. It depends on the detailed structure of the molecule. But that attractive force tends to force them in a very small volume, and that constrains where the individual molecules can be and puts them into some sort of crystalline structure. But they're still moving. There's still kinetic energy. We're still at a finite temperature here. And so they're bouncing around, but not bouncing enough to blast away from each other. If we heat it up, so we heat this solid, which means we're adding thermal energy. And our picture of thermal energy is going to be corresponding to kinetic energy down at that molecular level. They're not as tightly constrained next to each other, and individual molecules can start to wander around, even though the average density is still pretty close to the density it was in the solid. There's a little bit of extra space, and that allows molecules to move around, and they're not stuck next to just certain neighbors. That's a liquid. And a picture of a gas is if we heat it up even more, add more kinetic energy at the molecular level, the stickiness that's keeping them clumped together, they're moving so fast that they just, they do tend to tug at each other when they bounce off of each other, but the energies involved are just so big that they tend to spend a lot of time really far from each other. So they're not clumping at all in the gas. And of course, when we say heat, another way of saying that is we're increasing the temperature. Solid, increase the temperature, it goes to liquid. And by increasing the temperature, we're increasing the average kinetic energy of each of the molecules. And if you're increasing the average kinetic energy, they're going to tend to spend more time really close together where those electrons are really repelling. That's more potential energy too. So the potential energy tends to go up when the kinetic energy does. And if we increase the temperature further, they separate. They just have so much kinetic energy. Probably this isn't accurate. They should be moving much faster than is shown in this GIF that I stole from the web, but it would be hard to look at if that were the case. First property we want to talk about is expansion. So if we have solids or liquids, they tend to expand when heated. Now gases we can't really talk about the same way because a gas will tend to expand to fill any container you put it in. So the size of a gas, there's no well-defined size of a gas. You put it in a container, you make the container big enough, the gas will fill that container. That's just what gases do. But for solids and liquids, because they clump together due to that attractive force, we can measure the size and heat them up and see how much they expand along linear dimensions or how much their volume expands. Okay, and exactly how they expand depends on the substance. It depends on the details of those bonds and exactly how the bonds are made with the neighbors. Since it varies with substance, some substances will expand a lot when you heat them and some not so much. And this is the basis of the construction of a thermometer. If every substance expanded, if you heated it by 20 degrees Celsius, if it expanded by 1%, you wouldn't be able to construct a thermometer because not only would, here I've got some mercury inside a tube of glass. If the glass expanded by 20% and the mercury, alcohol, this is supposed to be a picture of an alcohol thermometer, the alcohol expanded by the same percentage, then everything would just sort of get bigger, but the alcohol wouldn't rise along the scale. So the fact that we can create thermometers relies on the fact that when you heat up glass, it doesn't expand that much, but when you heat up ethyl alcohol, it expands quite a lot. And so to create a thermometer, one of the first things you do is heat up the alcohol so it fills up this entire void, and then you seal off the top by heating the top so the glass melts together. And then you let it cool down. And because of that attractive force, the alcohol tends to contract in there, and we get what's essentially a vacuum up here. There's a little bit of alcohol vapor up there, but it's mostly a vacuum. And as you heat this up, it will expand up and down the tube. And the tube itself doesn't expand that much because glass doesn't tend to expand with temperature that much. Okay, so essentially a vacuum up there. It would be a mistake to put air up there because then as the alcohol expanded, you'd be compressing air. And in any case, that's not what we mean by a thermometer. What's the scale we're going to use, or one of several scales we'll use for thermometers for temperature. So we can stick this thermometer in a pot of boiling water and see the place to which the ethyl alcohol rises with a little bit of red dye in it to make it easy to see. And we'll mark that point as 100 degrees Celsius for water, right? And then we can put it in a pot of freezing water. Well, that means liquid water with ice that's been sitting in it for a while. So essentially it's the same temperature as the ice. And by definition, that's 0 degrees Celsius. And then we decide that there's 100 equal divisions between there. And that's the definition of the Celsius scale for temperature. I think the US is one of very few countries that still use Fahrenheit, but to me, I'm used to temperatures in Fahrenheit, and I always have to think a lot when someone gives me a temperature in Celsius to convert it to Fahrenheit. The construction's the same way, except somewhat less conveniently, the freezing point of water is 32, the boiling point of water is 212, and so there's a lot more divisions between the freezing point and the boiling point. Does anybody know the origin of why Fahrenheit, presumably, someone named Fahrenheit came up with this scale? It seems to me, sort of qualitatively, that a 1 degree Fahrenheit difference might be sort of at the very limits of human perception, that we could tell that difference. That might have been the motivation for making that smaller scale. But in any case, there's everyone who grew up in the US learns this back in junior high school or high school science, how to convert between degrees Celsius and degrees Fahrenheit. So those are two different scales. Neither one's the SI unit, but the Celsius scale is very close to the SI unit. And we'll talk about the SI unit later on. Not a surprise to most of you, because many of you have taken a lot of chemistry, at least. The picture of temperature. So, originally people didn't know what temperature was measuring, and they didn't know what hot and cold meant. We have a picture. We think of, oh, I'm imagining what's going on at the molecular level. But, back in the 19th century, people didn't, the atomic theory was not well regarded, and in fact, not believed by most scientists. So people believed that, most substances were probably like a continuum. And when you heated something, you were adding a substance to that substance, right? You heat something and there was a substance that was like a fluid called caloric that you put into it, and that was the stuff of heat. It was something different than other kinds of matter, but it was something that made things hot. So hotness was just some independent quantity. After the atomic theory, was finally accepted, people realized that you could think about temperature as, in some sense, as the average, related to the average kinetic energy of the molecules down at the molecular level. So it's telling you about the average 1/2 mv squared. Some of those molecules are going more slowly, some more quickly, but if you average them all together, you get something that's proportional to the temperature, or at least related to our SI unit of temperature that way. So higher temperature means molecules moving faster, essentially. When things, wow, that's really a weird color on this screen. When things, it looks much better on my computer, I assure you, but the projector is really lemon yellow and lime. When things heat up, of course, they're moving faster. And if you have two, if you take two masses, connect them by a spring, and you start them with a smaller speed, they won't oscillate that much. But if you start them with a bigger speed, stretch it and let them go like this, they're going to spend on average more time farther away from each other. And that's going to cause, if you think of a solid as being made of, this is supposed to be a picture of the adjacent atoms, or molecules that are bonded together here in the solid, or attracted together into the solid. As you heat them up, they're going to spend more time farther away from each other. So on average, the whole thing kind of dilates or expands like this. Same thing for liquids. Cold liquid, things are clumped together very tightly. As you heat it up, they expand further apart. So we want to quantify this, we want to have something that we can calculate with. And so here's a way that we can quantify how much something is going to expand. And we expect different substances are going to expand at different rates relative to how the temperature is increased. So I'm going to imagine I have, here we'll talk about first the linear expansion of solids. What I'm concerned of is if I have a chunk of a solid and I heat it up by so many, say, degrees Celsius, how does the length change? So here it is at a colder temperature, here it is at a hotter temperature. I've heated up by some change in temperature delta T, and we want to know what is delta L, or in other words, what's the relationship between the original length of the object and the final length at the hotter temperature. And here's some reasonable assumptions we might make. Alpha is a constant here. So we're saying the change in the length seems like it should be proportional to the original length of the object. Think about what that means. If I doubled the length of something, then when I increase the temperature by the same amount, I'm expecting it to get twice as long. If something is a nanometer long, when I increase this temperature, it's not going to increase by that much. But if I have a meter stick and I increase it by the same temperature, it's going to, expand by a substantial amount, not a microscopic amount. So the change in length is proportional to the original length, and it seems like it should also be proportional to the change in temperature as long as the temperature change is small. When the temperature change is small, even if the length, the length as a function of temperature is some nonlinear curve, if you're changing temperature along this axis in any small change region, it looks like it's a linear curve. So it'll be, the change in length would be proportional to temperature. Okay, and alpha is a constant that depends on the details of the material that we're talking about. We're only talking about solids here. You can't talk about the change in length of a liquid because liquid doesn't have a well-defined length. It just flows all over the place. But solids can have a well-defined dimension along its length or width, or whatever. So combining that together, this is the change in length. So if we want to calculate the new length is equal to the old length plus the change in length. So if I take L0 and add it to this, and then I factor out that common factor of L0, we get the new length is the old length times 1 plus alpha delta T. And alpha depends on the substance. So here's a table I think that you'll find in, I think I took this from Giancoli. It looks like Giancoli's kind of tables. Again, it's only relevant for solids. There's some liquids and gases down here, but this coefficient of linear expansion, alpha, is only listed for the solids. And you can see things which expand at greater rates. Aluminum expands a lot, right? Here's two different kinds of glass, ordinary glass and Pyrex. Why would we want Pyrex to expand less than regular glass? Yeah, I mean, because we use it to make, like test tubes and things out of, where you're putting it over a Bunsen burner. I'm sorry, I couldn't actually hear what you said.
Oh, I put it in the oven.
Yeah, it goes in the oven, same thing. If you take a piece of ordinary glass and you stick it in an oven and you slowly turn up the heat, it doesn't matter, right? Because the whole thing will just slowly kind of dilate and there won't be any stresses in it. What you don't want is to heat up one part of the glass and have another part of the glass stay cold. So that's like you put a regular glass casserole dish in there with an ice cold casserole in there. Maybe you took it out of the freezer. You put it in the hot oven. The outside of the glass heats up a lot, but the part that's right next to your cold casserole doesn't heat up so much. One part of it expands a lot, the other part doesn't. That's going to cause the glass to shatter. The more the substance expands, the worse that is. And so that's why Pyrex not expanding as much as ordinary glass makes it less likely to shatter when you put it in hot situations, because the hot part is going to expand less than the cold part. That's why in chemistry labs, you tend to have glass things made out of Pyrex, because you want to be able to heat them and not have them shatter. Notice that this alpha is in this table is listed in units of inverse degrees Celsius. So let's look down at our formula here. That means if alpha is in inverse degrees Celsius, I better put in my delta T in Celsius, and then this will have no units. That will make sense to add it to the one with no units. So the whole thing in parentheses has no units. And then when I multiply by a length, I'll get something that still has length units, right? So it all makes sense. So if you're using this table, and this would be the kind of table that would appear on your final exam with your equation sheet or something like that if you need to use it, just be familiar that you should be using degrees Celsius. Here is something called a bimetallic strip. What it is a thin piece of metal. Maybe I should show this on the board. Already moved my camera, sorry. It's two different kinds of metal that expand at different rates. Looks like we're out of focus there. Hold on. So I look at the table and I find one metal that kind of expands a lot with temperature, and I bond it to another piece of metal that maybe doesn't like to expand as much with temperature. What do you think is going to happen when I heat up this strip, which is just two thin pieces of metal put together? Change the temperature. Yeah. It'll bend, yeah, because I can't remember which one I said, but maybe this one has a large alpha. This one has a small alpha. And so this one, as I heat it up, is going to want to expand a lot. It wants to get longer, but unfortunately it's stuck to the other one. The way for it to get longer is actually to curl around into kind of a circle like this. Because the part with the small alpha will have a slightly smaller radius, and that means it's going to be slightly less length along that circumference there, whereas the outside one is going to have a slightly longer length. And so bimetallic strips do that. Let me just show you a bimetallic strip. I brought in a little Bunsen burner. Hopefully I don't hurt myself, and I should bring my camera back over here. Unlike the chemists, I'm not turning on the Bunsen burner in lecture every day. Okay, let's. Yeah. So I don't know which side is which side of metal, but it's two different pieces of metal bonded together. And as I heat it up, it tends to curl like that. And that can actually be kind of useful in that, well, nowadays thermostats are made with solid state materials, but back in not too long ago, if you looked at a thermostat in your house, it would actually use a bimetallic strip in the following sense. You could have a strip that was just open to the air in the room like this, right? And as the temperature in the room got colder, maybe it starts to curve in this direction. And at some point, there's a little electrical contact down there. When that piece of metal bends down, or maybe it's when it heats up, you know, you can design it different ways. When it bends down sufficiently, it closes an electrical contact. It meets up with another piece of metal, causes a current to flow, and that causes your heater to come on or your air conditioning to come on. So that's how all thermostats used to be made. Now they're made with solid state materials that are easier to control with electronics. Okay. So that's linear expansion.
Dr. Kelly,
Yes.
so do these new solid state materials detect temperature better?
Yes, you know, semiconductors often, you know, they change how well they conduct electricity very sensitively with changes in temperature. And so you can run a current through something and the resistance of the semiconductor will change wildly as the temperature changes. And so you can detect temperature changes very sensitively. And
Wow.
you know, the problem with these bimetallic strips is, well, you know, you get a little bit of oxidation on the surface there. It doesn't conduct so well anymore. So people had all kinds of things, you know, a lot of times to make this work a little bit better. I guess I'm not showing the screen, but there was another kind of thermostat that still used a bimetallic strip, but they realized, oh, the oxidation would cause problems. So what they would do is let me see if I can remember kind of how this works. You've got your bimetallic strip, and you've got a little, sort of cylindrical container in there. And you've got, maybe one electrical connection up there and one electrical connection down there. When those two are connected, your heater comes on. And you've got a little thing of mercury there, a little bubble of mercury. And if it's tilted up the way I'm showing it here, the mercury is going to sit on this side and the connection's not made, right? Mercury is a conductor, liquid metal. But when it bends down enough, the mercury will flow to the other side and make that connection. And then you don't have to worry about the oxidation so much at those. It makes a very good, reliable connection. So that was another way that people got around that. But generally, the solid state things are much more reliable for longer periods of time and more accurate measures. You can imagine this bimetallic strip is kind of bent and stuff like that. You can get metal fatigue after many years of use with the semiconductors. Well, probably you're going to replace your thermostat long before it wears out in any way, but you don't have to worry about things sort of getting fatigued as time goes on. Okay, so in the same way, we have linear expansion. Of course, if all three dimensions of this solid expand, the volume is going to expand. And it's related in a very simple way to the way it expands along one dimension. So as I heat this up, I'm going to expand all three dimensions. You're only seeing two dimensions here. Same assumptions as before. The change in volume is proportional to the original volume and proportional to the change in temperature. So you get a very similar thing that tells us the new volume in terms of the old volume. Same table from Giancoli, just the second one over here, gives coefficients of volume expansion. And again, they're in units of inverse degrees Celsius. And if you look at the formula, that will give us something that's unitless inside there. These are defined not just for solids, but also for liquids. And we're not going to worry too much about the gas. Here, they're holding pressure constant, but at least for these ones, we don't have to worry anything about what sort of state it's being held in. So let's just think about it as applying to solids or liquids for right now. We'll talk about gases separately later. And they tell us that certain things expand quite a bit. And in fact, what you'll find, if you do the math, it's a little bit more complicated than you might think, but all of these volume expansion coefficients are just 3 times whatever the linear expansion coefficient is. And that comes from multiplying 3 factors together and giving you a factor of 3 in front of it. Okay. And again, you got to use degrees Celsius. Here's something interesting about volume expansion. Sometimes people imagine, okay, so here's, we'll do this experiment. Here is a ring. And here is a corresponding ball. And the ball just barely fits through there. It's kind of hard to get it through, but it just barely fits through. Don't make a fool out of me now. Should barely, yep, there we go. Barely fits through the ring. So it's just almost exactly the right size to get through. If I heat up the ring, well, of course, if I heat up the ball, it's not going to be any surprise that I won't be able to get it through there if I keep the ring cool. What about if I keep the ball cool and I heat up the ring?
It'll be easier to get the ball through.
Easier to get the ball through? Some are shaking their heads yes and some no. What would be the argument against that? Austin? Right. I mean, if it expands, maybe it's just going to get thicker all the way around and the hole will get smaller. Okay, that seems reasonable too. But maybe the whole thing just gets bigger. Let's look at the picture of the, my crude lemon-colored picture of the, whoa. Now it's really not going to go through. My crude picture of the molecules expanding here. You can convince yourself that although many people think, naively, that it's going to be like Austin was suggesting, that the hole in something is going to expand inward because everything would expand. Wouldn't there be more room to go in? Just look at this picture and imagine something with, a little, here I've made a bowl out of this, down at the molecular level, and I heat it up. If everything expands, pushes against its neighboring molecules, actually the void inside expands exactly the same way as the molecules themselves expand. So when you expand a metal container, if you heat it up, it's just going to get bigger. The inside gets bigger and the outside gets bigger. Everything gets bigger. The volume measured from the outside and measured from the inside gets bigger. Let's try it. We'll have to let this heat up for a few minutes. Well, more than a few seconds anyway. I'll adjust the camera in just a second. All right, got my Bunsen burner on. Let's see, let's heat up. We'll do the non-exciting one first. Did this go out? Yeah, it did. Huh. Got it on full. That's kind of weird. I need to adjust my Bunsen burner. Be the end of my experiment. There we go. I just didn't have it turned up enough. So we'll heat up the ball. It'll be pretty clear it doesn't go in. And then the exciting part is hopefully I can heat up the ring and make it go through easily. All right, so heating it up a little bit. Okay, it's gotten a little bigger. Still looks like it might go through. Oh, this is exciting. All right, so it's not even close now to going through. I mean, it doesn't even get close to going through the middle. So let's let this one cool off a little bit and I'll try to heat up the ring. We'll see if we can get it to go through easily. If it goes through easily, then it seems likely that, Austin's hypothesis, which I agree is quite compelling, that the ring would shrink inward. It doesn't seem to make sense when you look at that crude molecular picture of a solid, in that everything dilates. That's going to make the void dilate too. See if that's enough. Oh yeah, look at that. All right. It just depends, these are both made out of the same kind of metal, so they're supposed to expand at the same rate. But yeah, I mean, certain metals will expand faster with temperature. So it probably would be a more confusing thing to think about if we had two different kinds of metal that these were made of. But yeah,
I feel like just added heat to one side of that thing, but it like oval.
Yeah, I mean, it probably wouldn't stay a circle anymore. But so it's may or may not fit through. I don't know if the answer to that question of what would happen when I try to put it through would be easy to figure out. Try not to melt the new countertop in here. All right, and I think we're supposed to do. Did the ball and loop? Yes, worksheet. Okay. Let me grab a worksheet here, which has to do with a steel tank that's filled to the very top with gasoline, and we're told the original temperature, and then it sits out in the hot sun and increases to 40 degrees Celsius. So it goes from 20 degrees Celsius to 40 degrees Celsius, and we want to decide how many gallons of gasoline will overflow. This, we have to look at our table, and I think I put the table on the back side of this. I have your coefficients of linear and volume expansion on the back. Which do you think, if we expect the gasoline to overflow, which one has the bigger coefficient of volume expansion? The steel or the gasoline? Yeah, the gasoline is going to expand more. If they expanded at the same rate, then it would stay full all the way to the top. So the idea is we filled it to the very brim, but if the gasoline expands more than the steel, and in this case, we expect the void inside the steel tank to expand exactly the same amount as a solid steel object was, just based on that kind of picture I was showing you. So even though it's not a solid steel tank, we can assume that the volume inside is going to expand the same way as a solid steel tank would. So look up the coefficients for gasoline and steel on the backside. Calculate what the final volume of the gasoline would be and what the final volume of the tank would be, and see what the mismatch is there. If you're there, I get 0.329 gallons. About a third of a gallon. Okay, let's run the numbers through together here on the board. So here's our, what tells us if they're both starting with the same initial volume of 18 gallons, right? We have the steel void and also the gasoline take up an initial volume of 18 gallons. And we want to figure out what their final volume is. So I'm going to do it separately for the gasoline and for the tank, the void inside the steel tank, which is going to expand the same way as the steel itself. Both of these start out at 18 gallons, right? We filled up an 18-gallon tank exactly to the brim. So the volume of the tank is exactly equal to the volume of the gas, but they have different coefficients of volume expansion. If I look up gasoline on the table, I get beta is equal to 950 times 10 to the minus 6. And delta T here, I think, was 20 degrees. It went from 20 degrees to 40 degrees, so delta T is 20 degrees Celsius. I should have put, this has units of 1/degrees Celsius. Since we're technically not using SI units, it's best to be careful and leave them in there, but they do cancel out. So the things inside the parentheses are a pure number. Whereas this one, for the tank, the volume coefficient expansion of steel is beta equals iron or steel 35 times 10 to the minus 6. Quite a bit less than gasoline, right? 1/degrees Celsius times 20 degrees Celsius. And then all I do is calculate the bigger volume of the gas minus the smaller volume of the tank at the higher temperature. And when I do that, I get 0. So this was 18.342 gallons minus 18.0126 gallons. Those are the numbers I got individually for those. And when you subtract them, you get 0.329 gallons. So about 1/3 of a gallon overflows. Questions on that one? All right. That's linear and volume expansion. Okay. Now, what about gas? Well, again, gas is a little bit more complicated in that it doesn't have a well-defined length. It doesn't have a well-defined volume. If you put gas in a container and you make the container bigger, the gas will just fill it. So it doesn't have a well-defined volume. But there is, if we want to know something about the volume of a quantity of gas, you have to know several things about it. Its temperature and its pressure is one way to know the volume of the gas. So if you have a certain quantity of gas, you need to know what the temperature and pressure is. And the question we want to address now is, what's the relationship between volume, temperature, and pressure? Many of you have seen this before in your chemistry classes or physics classes. We're going to, consider what's called an ideal gas, where the individual molecules don't interact much with each other, but rather most of what they're doing is banging into the sides of the container. Okay, so we're going to look for a relationship that tells us how the number of molecules of gas that we have, the temperature of the gas, the pressure of the gas, and the volume of the gas are all related. And along the way to that, we're going to look at how this relationship was developed historically was through what are called the gas laws, which are sort of telling us partially about these relationships between those 4 variables. And then we'll put them all together to get the ideal gas law. How does volume vary with pressure, or how does pressure vary with volume? I mean, pretty clearly they're related. If I make the volume smaller on a gas, the pressure seems like it's going to go up, right? If I let it expand to a bigger volume, the pressure is going to go down. Boyle's law is just an experimental determination of that. And just to be very clear, we're talking about keeping the same amount of the gas. We're not adding molecules during this process of changing the pressure and the volume. And we're keeping the temperature constant because, if I compress the volume, but then I cool it off, maybe that would counteract the smaller volume and keep the pressure constant. So we got to actually say what's constant here. So we're going to say, how does volume vary with pressure at constant number of molecules in the gas and at constant temperature? And the question is answered experimentally through Boyle's law. The volume is inversely proportional to the pressure, and that at least makes intuitive sense. The bigger the pressure, well, the smaller the volume, the bigger the pressure. That seems to make sense as long as you're keeping the temperature constant and you're not changing the number of molecules. Here's a way to sort of make it look more than just, roughly appealing. Imagine that, again, we're considering something that's sort of a dilute gas, and we'll call it an ideal gas. We're going to pretend, or at least make the gas dilute enough, that those molecules only very rarely run into each other. Mostly what they're doing is running completely through all the other gas molecules, and then they hit the side of the tank. So they're bouncing around inside whatever vessel they're in, but they essentially don't interact with each other. They're just bouncing, rattling from one side of the tank to the other. And of course, the pressure is determined by how often and how hard they're hitting the side of that container. So here I'm imagining I have a certain volume of container, and we've got a little piston at the top, and we can determine what the pressure is. So maybe we're pushing with a certain pressure at the top, and it causes it to be at this particular volume. And we're keeping it in a temperature bath, so it's maintaining constant temperature. Now let's imagine we keep that temperature constant, but we double the pressure. Well, let's think about it this way. Suppose we have the volume, but I keep that temperature constant. Here, maybe it takes, I'm just making up numbers, maybe it takes 1 microsecond for it to bounce between the walls. If we keep the temperature constant, but I make this distance smaller, that means the average speed of these molecules is going to be the same, and that means it's going to be hitting that top surface twice as often as it was, right? In a given amount of time, it's going to hit that top surface twice as many times as it would over here, because it's got a longer distance to go and it's going at roughly the same speed. So we will double the pressure. In that approximation where we're pretending the molecules don't hit each other, they're just rattling against the edge of the cage. If I take it to 1/3 of the volume, they're going to hit 3 times as often per unit time, right? 3 times as many strikes, and that's going to triple the pressure. So what that's saying is, as you double the volume, you're going to have the pressure, and that's the same as this relationship. So that's Boyle's law. That's just one piece of the puzzle. How does volume vary with temperature? Again, we're going to answer the question experimentally, and we have to be careful to specify, no, we're not going to allow any new molecules to get in there. The total number of molecules that's being denoted by N here is going to stay constant. And in this case, we're going to keep the pressure constant. So if we increase the temperature, if the pressure is going to stay constant, maybe we have to increase the volume as well, right? Generically, if you have a fixed volume and you increase the temperature, you're going to increase the pressure because things are going to be rattling against the edges more quickly. But if we increase the volume, we might be able to counteract that. So let's keep the pressure constant in this case and see how volume varies with temperature. Experimentally, it's found to be a linear relationship. As you increase the temperature, you have to have an increasing volume in order to keep the pressure constant. If you didn't increase the volume, the pressure would certainly increase. So if we're going to keep the pressure constant, we're going to have to increase the volume. Whether it's linear or not just depends, on experimental results. That's how we're thinking of it here, just as an experimental thing. Now, we can't keep going. Of course, if we decrease the temperature too much, here we're talking about a gas. The gas will eventually condense into a liquid and maybe a solid as we keep going down. And so we're not going to be talking about laws that talk about a gas for very long. But over a certain range of temperatures, we might be able to get data, and it's linear in that region. And so it's sort of tempting to sort of extrapolate down in that direction and find where it crosses the 0 volume line on there. And it turns out, experimentally, if you do that, take this data up here and just follow that line, extrapolate out, you would find that the volume would go to 0 at a temperature of minus 273.15 degrees Celsius. And amazingly, that's true for all different kinds of gases. You take nitrogen gas, take argon gas, all of them are going to give the same result. So this temperature seems important. We're going to call that temperature absolute 0 and use it to our advantage, because notice this relationship of volume with temperature in degrees Celsius is sort of, it's not too complicated, but I have to use something like y equals mx plus b because it's got a non-zero y-intercept at 0 temperature. Whereas if I call this my 0 temperature down here, then it's simply saying that volume is proportional to temperature as long as I measure that temperature relative to minus 273.15 degrees Celsius, or relative to absolute 0. So we're going to define our new and SI temperature scale to be temperature measured in Kelvin. And Kelvin temperature is just the same spacing as degrees Celsius temperature, but you add on 273.15 to it. So 0 degrees Celsius, which is the freezing point of water, is 273.15 Kelvin in that scale. Okay, and the motivation is, look, now the volume as a function of temperature doesn't have any y-intercept. So it's just saying the volume is simply proportional to the temperature. Okay, that's our rule. And that's called Charles's law in the history of developing these gas laws. Again, totally experimentally determined. But that also helps us get our SI unit for temperature. Okay. You know, it's Charles's law. We can sort of make it at least intuitively appealing, not maybe as quite as clear as the previous picture. Okay, so it's saying we're going to keep pressure constant and the volume's got to go up as we increase the temperature. So as I make these things move faster, they're going to be rattling back and forth faster. But if I increase the volume proportionately, it is going to take longer for them to bounce against the surface. So apparently, increasing them in the same proportion. If you increase the temperature by 1%, you got to increase the volume by 1%. That's Charles's law. Here's a third law that, as far as I know, doesn't have a name because it's sort of unremarkable and it's very intuitively true, hopefully. We haven't talked about the relationship of any of these three variables to n yet, the number of molecules in your gas. And hopefully it's intuitively appealing that if we keep the pressure constant and the temperature constant, that the volume required to keep those two constant is proportional to the number of molecules. So, right, if I have a certain number of molecules in a volume, if I double the number of molecules, I better double the volume if I'm going to keep the pressure and temperature constant. If I doubled the number of molecules in this same smaller volume, wouldn't I increase the pressure, right? So, you know, if you just add in double the number of molecules, you keep them at the same temperature, then you're going to keep pressure the same on all the surfaces. It's just like a bigger volume at the same pressure, and the temperature would be the same too. So the volume is simply proportional to the number of molecules. Okay, I know, not so fascinating. This is experimental stuff back in the 19th century sometime when people were investigating these kinds of things. I think, I don't know, maybe earlier than that. What can we conclude to these? We want to put them together into a single law that many of you have seen before, the ideal gas law. Okay, so the fact that volume is proportional to temperature, that means volume is equal to a constant times temperature. But, you know, since this law is true only at constant N and P, constant number of molecules and constant pressure, that constant of proportionality, when we say V is proportional to T, could actually be a function of N and P. Right? If N and P are constant, we're saying that V is proportional to T, but that constant might depend on N and P. So we got to figure out what that unknown function of N and P is. Let's combine it together with the second law. V is proportional to 1 over P. If V is proportional to 1 over P at constant N and T, well, we've already got the T dependence factored out here, but V should be proportional to 1 over P. And that means that this constant here, which is really a function of N and P, should be 1 over P times some other constant that might depend on N still. And then we put in the third law, which as far as I know doesn't have a name. V is proportional to N at constant P and T. So if I keep P and T constant, V better be proportional to N, and that means that this constant should be a true constant times N. Okay, solving that for P times V, which is the traditional way of expressing it, this says that P times V is some constant times the number of molecules times the temperature in Kelvin. Remember, our law up here for V versus T is assuming that we're measuring things relative to absolute zero. So we got to use our SI unit Kelvin when we're plugging in down here in the ideal gas law. Okay, So that's called the ideal gas law, and it tells us how the pressure, volume, number of gas molecules, and temperature are related to each other. And the constant K is determined experimentally to be 1.38 times 10 to the minus 23rd joules per Kelvin. Okay. And again, that symbol capital N, I know you don't use this as much in chemistry, but chemistry, you use the number of moles, but N is actually the number of molecules in the gas. So that's going to be a huge number, maybe something like Avogadro's number on that order that would be in a reasonable volume of gas. Okay, now, amazingly, you might think that this constant of proportionality that we put into all that business, K, would depend on what variety of gas we were using. It might have depended on the mass of the gas molecule. So nitrogen would be different than argon, would be different than, helium or something like that. But it doesn't. Experimentally, that was a surprise, and that's we'll have an explanation for that a little bit later on, but I'm seeing we're out of time now. And so maybe we'll go on and re-express this in terms of moles on Monday. We're almost done with this chapter. I told you we're going to do a sort of a very short overview of this stuff. So there's probably some things in the end of chapter 13 that we're not going to talk about. So keep in mind what we're talking about, and it's probably not everything in that chapter.